Hello, this is Professor Kuehn, and welcome back to Electricity, Magnetism, and Light, the course at Wisconsin Lutheran College. We have been talking about the work of Charles Coulomb and his work with electrical repulsion, specifically the law of electric force that he developed. Now what we're going to do is move on to the work of Hans Christian Oersted. The reference here is A Student's Guide to the Great Physics Texts, Volume 3, Chapter 7. And this text is from a paper that Hans Christian Oersted wrote called Experiments on the Effect of a Current of Electricity on the Magnetic Needle. I want to start with a few introductory comments about Hans Christian Oersted. So I'll be reading from the introduction in the book. So far, we have explored magnetism and electricity as really separate phenomena. This is the legacy of William Gilbert, who recognized that while magnets and electrically charged bodies can exert forces, they do not exert forces on each other. Electrically charged bodies attract or repel other electrically charged bodies, while magnetic bodies attract or repel other magnetic bodies. This very simple and pleasant demarcation or separation was really upset by the work of Hans Christian Oersted, who lived at the end of the 18th century and the beginning of the 19th century. He was born in Denmark. After early homeschooling, which included the study of many languages, he entered the University of Copenhagen to study pharmacy, like his father. In 1799, he pursued a dissertation with the imposing title, Dissertation on the Structure of the Elementary Metaphysics of External Nature. He was actually heavily influenced and reacted to the recent work by Immanuel Kant. He received very high academic honors in philosophy, and afterwards he worked for a short time as a lecturer and a pharmacist before obtaining funding to travel to Germany. While there, his contact with Johann Wilhelm Ritter drew him into the experimental study of physics and chemistry. And so in 1806, he accepted a position as a professor of natural philosophy at the University of Copenhagen. He published dozens of scientific papers in several languages, in his native Danish, in English, in French, German, and Latin, on various topics in chemistry and electricity and acoustics, thermodynamics, and mechanical properties of substances. He was also an accomplished writer and poet, and a close friend of the fairy tale author Hans Christian Andersen. Today, Oersted is best known for his discovery of the connection between electrical currents and magnetism. This work, which is described in the reading selection in this chapter, inspired later experiments on electromagnetic phenomena by both Michael Faraday, we'll come across him a little bit later in the semester, and Ampere. And these really culminated in the work of James Clerk Maxwell and his electromagnetic theory of light. But we're getting ahead of ourselves, so why don't we jump right into the text and try to understand Oersted's famous experiments. So this begins on page 76 in the text. So what does he do in this text? Well, the first thing that he does is he begins by talking about the people who were present, the individuals who were present during his experiments. So he mentions people like Mr. Vliegel, Knight of the Order of Dannenberg, and Mr. Reinhardt, a professor of natural history, Mr. Jacobson, a professor of medicine, and so on. He mentions a number of people who are there witnessing his experiments. So what are the experiments that Oersted carried out? Well, he carried out a number of experiments, and he documents them in this text. What I find, most difficult about this text is he doesn't have any drawings. So what I'm going to do is try to supplement his text with some artist conceptions of what his apparatus might have looked like. So he begins in the middle of page 77 by talking about the galvanic apparatus that he used. So let's talk about Oersted's galvanic apparatus. Today we would simply call this a rudimentary battery. A galvanic apparatus. Okay, what is it made of? Well, how does a battery work? What he did is he mentions that he takes copper and zinc plates. So I'm going to make a sketch here. This is supposed to be a zinc plate. He gives the dimensions of these. They're 12 inches by 12 inches, if I remember correctly. And he dips them into a trough. Okay, so imagine a couple of parallel plates. This one on the right is made of copper. The one on the left is made of zinc. And these are placed into a trough. I guess he gives the dimensions of the trough. He says that the trough is 12, the length and height of each is 12 inches. The breadth scarcely exceeded 2.5 inches. It's kind of 2.5 inches wide and 12 inches tall and deep. I guess it doesn't look like that in my diagram, but nonetheless, that's the case. And there are 20 of these troughs. Okay, so I'm going to draw maybe one more just so you get the idea. And in, like I said, in each of these troughs, there are alternating zinc and copper plates. And for those of you who might have studied a little bit of chemistry, you might recognize these as a battery. Each of these is an individual battery. So the troughs are filled with water. And the water had mixed in with it, he says, sulfuric acid, 1/60th of its weight sulfuric acid, and an equal quantity of nitric acid, so 1/60th of its weight nitric acid. Okay, so there's a combination of water and acid. And if you do this, there are chemical reactions that are carried out between the surface of the copper and the acid and the surface of zinc and the acid, which causes electrical charges to build up on the copper and zinc plates. So what happens is the copper plate, due to these chemical reactions, acquires a positive charge, and the zinc plate acquires a negative charge. And what can happen, so first of all, how would you know that this is happening? How do you know the copper plate acquires a positive charge and the zinc plate acquires a negative charge? Well, one could simply do the same kinds of experiments that, for example, Benjamin Franklin did. He could touch a small pith ball, a small cork ball to the copper plate, and another small pith ball to the zinc plate, and then you would notice, having done so, that those two balls attract each other. That is, they must have acquired opposite charges, one positive and one negative. You could likewise touch both balls to the copper plate and find that they repel one another. All right? So one can deduce by these electrostatic experiments that there is a charge accumulating on these copper and zinc plates. But nonetheless, it's a fairly small charge, and it depends on the specific concentrations and types of acid and what kind of materials you put into it, copper and zinc. But you can amplify this effect by attaching these copper and zinc plates in series. So if you take a conducting wire and connect the copper plate of one trough to the zinc plate of another, and then attach the copper plate of that one to the zinc plate of the next one, like this, you can make an array of these of arbitrary length, and you can make a larger and larger charge difference appear between the ends of the battery. So the more troughs you use, he says he uses 20, you can get a fairly significant charge difference or voltage difference between the two ends of this battery. This elementary form of a battery, which must have taken up quite a bit of space, you have these troughs of acid on the floor in the laboratory. Nowadays one can make very tiny batteries, but they operate on essentially a very similar principle. And if you look at modern day electronic circuits, there's a symbol for a battery that looks like this. This is the schematic figure for a battery. So this is a modern schematic representation of a battery. It could be a different kind of battery, different kinds of materials. Nonetheless, it has the same representation. And these lines represent these stacks of different plates, copper, zinc, copper, zinc, copper, zinc, copper, zinc, and so on. And then you'll have a positive charge on this end and a negative charge on this end. And then you can hook this up into a circuit of some sort and drive electrical current through this circuit. Okay, so that's kind of jumping ahead into what we're going to come across later in the semester. Anyhow, why did he build this? This isn't the first galvanic battery that was created. Nonetheless, he used one of these, and the point is that he connected the ends of this battery to a wire. Okay, so let's look at, this is the next paragraph. He says, let's suppose you take this whole battery. I'm going to represent this battery by a little box that looks anachronistically like a car battery. So imagine a couple of terminals on the top of this battery. Maybe it's a 12-volt battery like a car battery. Make it look like a box. But by this, I mean this whole apparatus right here. So we've got this battery. And he hooks this up to what he calls a uniting wire. So I'm going to draw a wire right here. It's a nice straight section of wire. I'm going to draw it extra thick so it looks kind of like a rod. And this, you might imagine, he puts on a stand that sort of holds it like this. So I'll draw a couple of stands that hold this up. Draw another one over here holding this end up. You'll see where I'm going with this in a minute. Okay, and then he has this uniting wire hooked up to this end, and the other uniting wire hooked up to this end. And let's suppose this is the positive terminal, or the copper terminal of the battery, and this is the negative terminal, or the zinc terminal of the battery. So this is the uniting wire right here. And what he does is he orients this apparatus in a particular way. So I'm going to draw some compass directions here. So this would be the northerly direction. This would be the eastward direction. This would be the westward direction. And this would be the southward direction in the laboratory. So this wire is oriented along the north-south axis. And he mentions, so he says, the opposite ends of the galvanic battery are joined by a metallic wire, which for shortness sake we call the uniting conductor or uniting wire. To the effect which takes place in this conductor and in the surrounding space, we shall give the name of the conflict of electricity. So there's something that's going to be going on around this uniting wire that he is going to call the conflict of electricity. This is a term that he coins, electricity. Conflict of electricity surrounds this wire. And he's going to be talking about why he thinks there's a special, I guess, environment around this uniting wire when you hook it up to a galvanic battery. Okay, so he says, let the straight part of this wire right here be placed horizontally above a magnetic needle, suspended properly and parallel to it. So you might imagine taking a string around this and hanging a compass needle like this. I'm going to draw the pointy end like that, pointing in the northerly direction. And he mentions that, and here he says, this being the state, the needle will be moved and the end of it next to the negative side of the battery will go westward. So here's a negative side of the battery, and the end of the needle that's near that, when you attach these wires to it, suddenly swings in the westward direction. So the tip of the needle, when the uniting wire is connected, to the terminals, to the battery terminals, swings westward. Okay? All right, he says also that this happens if the distance of the uniting wire does not exceed 3/4 of an inch from the needle. The declination of the needle makes an angle of about 45 degrees. So if I were to look at this from the top, so let's look at a top view of this uniting wire. All right, and if this distance between here and here, I'll call that distance right here D, maybe I'll call it H, the height is around 3/4 of an inch. Okay, so that's 3/4 of an inch away. That being the case, he says the angle between the needle and the northerly direction, so that's the northerly direction, will be about, so that angle right there, he says is about 45 degrees. Okay. If the distance is increased, he says the angle diminishes proportionally. So the angle of the needle depends on the distance. From the wire, right? That's an important experimental observation. And he says it depends on the distance from the wire. And he says its angle, the declination he calls it, likewise varies with the power of the battery. So if we used a more powerful battery, this would be a larger angle, and a less powerful battery would produce a smaller angle. Okay, so this is the first experiment that Oersted carries out. And it seems, just to emphasize this, it seems like this provides a connection between electricity and magnetism. After all, magnetic needles previously only reacted, as far as people had observed, to the magnetic poles of the Earth or the poles of other magnets. Notice he doesn't have any other magnets around here, except of course the Earth, which is orienting the magnetic compass needle in the north-south direction initially. But suddenly when you hook up an electrical battery, suddenly the magnetic needle turns. So there's something very strange going on here. And what Oersted is going to do is try to make sense of this observation.